Hi folks, welcome back to our videos for this week, I guess. So this week we're going to start out with a concept called a subspace, but to help us out, I want to remind us of two important concepts that we talked about last week. So I've got them over here, super teeny tiny, so hopefully you can see them. But big, super important concept from last week, right? Vector spaces. So a vector space is a set along with an addition and a scalar multiplication, and the addition and that multiplication have to satisfy certain rules, right? So the addition has to be closed, commutative, associative, there's got to be an identity, and there have to be additive inverses. The scalar multiplication also must be closed, and it has to satisfy two distributive properties here. It also has to be associative, and 1 times the anything has to be the anything. Then we also talked about spans of different sets, and a span is just all the linear combinations that you can make out of your objects. It's anything that you could make out of your base objects in your set. So today we're going to be talking about, or in this video, we're going to be talking about kind of mini vector spaces within the larger vector space. And hopefully, if we have these little mini spaces, we're not going to have to always look at 10 axioms to prove that something is a vector space. Our goal is to try and reduce our work a little bit. So let's start out with a definition where we describe what that like mini vector space will be. So we're going to start out by letting V be a vector space. A subset W of V, so W is a subset of V, is a subspace of V if AX plus BY is an element of W for all A, B in R, and for all X, Y in W. So what this definition is telling us is if I have a subset of my bigger, so I have a vector space to start out with, and I pull some vectors from that vector space. If any linear combination of the vectors I pulled is also in that set, then that set is a subspace. If I could find a linear combination of those vectors and it's not contained in that subset, then that subset is not a subspace. So we're also going to have a theorem to kind of go along with this definition. It's a noisy pen cap to sort of enhance this definition of subspace. So we're going to write that just underneath. This is going to be theorem number 6. And this says we're going to let W be a non-empty collection of vectors. So we're going to say let W not equal to the null set, right? So this means W is not empty. Be a collection of vectors in a vector space V. Then W is a subspace if and only if, so remember IFF means if and only if, W satisfies vector space axioms. Using the same operations as those defined on V. In other words, a subset is going to be a subspace if it satisfies all of these axioms. So we could determine if a subset is a subspace by checking to make sure all linear combinations are available there, or by checking off all of these vector space axioms. Now, remember, our goal here is to try and limit our work, reduce our work. So checking 10 axioms is not, going to cut down on our work. But there's some good news. Because W lives inside this bigger vector space V, it inherits certain properties. For example, in V, we know that the addition is commutative, which means we know that the addition for W is going to be commutative because W lives in V. So if I'm checking to see if a space is a subspace of a given vector space, I don't have to check that it's commutative because we already know that by the nature that V is commutative. Same thing with associative. Now, the other three additive axioms we do have to check because W is a subset. It doesn't contain necessarily everything that's in V. So W might not be closed. It might only have some things in it. And if it's not closed, if it's not all like self-contained, right, then it's not going to be a vector space. Similarly, if the additive identity is not included in W, then it's not a vector space. And if everything doesn't have its inverse, it's not going to be a vector space. So we can do a similar sort of treatment for the scalar multiplication axioms. We're going to have to check to make sure it's closed under scalar multiplication. But these two distributive properties and the associative properties get to be inherited. So these three are nicely inherited. And in fact, so is the fifth one, 1x equaling x is inherited because we know those things to be true in V. So we can take all 10 of those axioms and bring it down to, it looks like 4 things. And in fact, we're going to be able to write it in such a way that it's only 3 things. So that's what we're going to do. We're going to summarize this in a theorem that in order to check if something is a subspace, you really only have to check 4 things, which we're going to condense into 3 things instead of having to check all 10 of these. So let's write that on the board, but I got to make some space first. So we'll do some fancy editing magic. Ta-da! So here's our theorem. This theorem is so important it gets a name. So this is our subspace test. So suppose you have a subset of V. To determine if that subset is a subspace, here are the 3 things you have to check. So let's check them against our list over here. So the first thing we have to check is to make sure that the additive identity of V is also contained in W. So that means we're checking this piece, that we have an identity. Then for any vectors W and V, we have to make sure that their sum is also contained in W. So here we are making sure that it is closed. And then for this third one, we have to make sure for any vector W in W, AW is in W. In other words, any scalar multiple is contained in there. So that's making sure that our scalar multiplication is closed, which means we're kind of leaving off this one here, right? That we have our inverses. But remember how we're denoting our additive inverses, right? So it's like if there's V, then there's also negative V. So negative V is going to be -1 times V. So that's going to be our additive inverses are kind of consumed by number 3 over here. So if we're going to see if something is a subspace, we have to check these 3 things, and then we're going to be good to go. So let's do an example of determining whether or not a subset of a vector space is a subspace. And we'll use the subspace test to do that. Okay, for this example, we're going to be looking at a potential subspace of M22. So we have this collection of 2x2 matrices, and I'm noticing that there's a particular condition given here. So this specific collection of 2x2 matrices has to satisfy the condition that the two row sums are the same, right? So A plus B has to be the same as C plus D. And we want to know, is this a subspace? Does it meet our subspace criteria? So let's work through each of these three tests to make sure it meets them or not. So the first test is 0 there. So we know that if we are adding matrices, that the additive identity is going to be the 0 matrix. So we're going to have 0, 0, 0, 0. So we have to check in particular that this condition is met, because 0 is a real number, so we're good with that piece. So if I add these two here, 0 plus 0, and I add these two here, 0 plus 0, are those indeed equal? Yeah, 0 is equal to 0. So the 0 vector, the 0 matrix in this case, is included in W. So therefore, 0 matrix is an element of W. So we pass our first test. Hooray! Now we just have to check the second and third test. So we have to see if I have two vectors that are here in this set, is there sum contained in there? So let's let A, B, C, D and E, F, G, H be elements of W. So we've got these two 2x2 matrices, and we're going to say, let's let those be elements of W. So what it means to be an element of W is you have to satisfy this condition. So we know that A plus B has to equal C plus D. And we know that E plus F has to equal G plus H. So now what we need to do is we need to find the sum of these two generic matrices and see if the sum, the resulting matrix, satisfies this condition. So let's add them and see what we get. So we have A, B, C, D plus E, F, G, H. Well, that's just going to equal A plus E, C plus G, B plus F, and D plus H. So now what we need to do is we need to see, is this sum across the top equal to the sum across the bottom? So in order to do that, what I'm going to do is I'm going to start out with the sum across the top, use this relationship, because this is what we know about those variables, to see if I can take that expression and bring it to the sum of these two values here. So I'm going to start out with A plus E plus B plus F. That's going to equal. Now, when I know stuff about these, I want to have the variables from the same matrix grouped together. We can do that because these are real numbers and real numbers are associative. So we can regroup and they're commutative, so we can change order. So what I'm going to do is I'm going to group the A and the B together and the E and the F together. And those are just real number properties that allow me to do that. Now, ultimately, I need to introduce C, G, D, and H. So I know that A plus B is the same as C plus D. This is our condition for this set. So I know that this is C plus D. And similarly, I know that E plus F is G plus H. And that, again, is by the fact that these two matrices that we picked were elements of this set, so they meet that criteria. Now I'm going to see if I can regroup, so I get C plus G and D plus H, which I can do. Here's C plus G, and then D plus H. So we have that A plus E plus B plus F the row sum for the first row, is the same as C plus G plus D plus H, the row sum for the second row. So therefore, if I add these two matrices, A, B, C, D, plus E, F, and G, and H is an element of W. It meets the criteria that W has set. So we've proven now that we satisfy condition number 2. So we are closed under our addition. This now just means that we have to show that we are also closed under scalar multiplication. So I'm going to have to erase to give myself some space here. But this one's going to feel very similar to number 2. So 3 is KV there. So similar situation, we're going to have to start out by picking a vector that's in our space. So we're going to let AB, CD be an element of W, which means that A plus B has to equal C plus D. So now we're going to look at K times that, A, B, C, D. And when we multiply a matrix by a scalar value, we multiply each of those entries. So we're going to get KA, KB, KC, and KD. So as we did before, now we have to determine, now that we found what K times the vector is equal to, we have to see, does it exist in this set? In other words, do these rows meet the correct condition to be in that set? So I'm going to start out with the top row sum here. So I have KA plus KB equals. Now, again, the only thing that I know that's going to be able to help me out is this condition here, that A plus B is the same as C plus D. So I notice that these two terms each have a factor of K. So if I factor that out, I can end up with A plus B, which is nice because I know that A plus B is the same as C plus D. And now I can distribute that K to the C and the D, which is what I needed to show because that's the second row here. So therefore, K times A, B, C, D is an element of W. So we've shown that W meets this third part of the test. So yes, W is a subspace of M22. There we go. Okay, so now that we've kind of got an idea about what subspace is and a quick way to check to see if we have a subspace, let's see what this has to do with our friendly neighborhood spans. So we're going to state a couple of theorems and then we're going to do one more example for this video. Okay, so let's look at these two theorems that I've written up on the board. So theorem 8 says that V is a vector space and W is the span of some vectors. Doesn't matter how many vectors they are, just a span of some vectors. Then W is a subspace of V. So what this means, sort of the main takeaway that you want to like keep in your brain is that spans, oh, that's not writing very well. Let's try that again. Spans are subspaces. So what this means is if we can take our set and write it as the span of vectors in a bigger vector space, then we will know automatically it's a subspace. And this makes sense because spans are linear combinations of things, right? So a span is, if I have a span of like 3 vectors, then that set is going to be all the linear combinations of those three vectors. And our initial definition for a subspace is a set, so that if I have any two objects in it, a linear combination of them is also contained in the set. So that's basically cooked up to say that spans are subspaces. Okay, so if we see a span, we can automatically assume that it's going to be a subspace. The second theorem I have here, theorem 9, says let's let V be a vector space with W equal to the span of some vectors. And suppose U is a subspace of V, so that U contains the vectors that define this span. Then W is a subset of U. What this means at its heart, notice that W and U are not fully the same. So W is the span of this collection of vectors. So I give you some vectors and you make all the linear combinations out of it. That's W. What this is saying is if all I do is give you those vectors, none of the linear combinations, if I just give you those vectors to start out with, then that whole span is going to be a subset of U, of that subspace U. Again, this kind of makes sense because of the linear combination idea, right? So these are all the linear combinations of those vectors. If U is a subspace, it has to contain all those linear combinations. So it has to contain that span of those vectors. However, what this means for us, kind of our big takeaway from this theorem, is that to check containment of a span, you just need to check the defining vectors. Okay, that's what this piece here is saying. I don't have to check every linear combination of these vectors to see if it's in the subspace. I just have to check, does it have those like defining vectors? And if so, then I automatically get this containment that all of the linear combinations also get to be contained in that set. This theorem in particular is going to be really, really helpful if I want to show that two subspaces are the same. So we've seen already that when we have like a spanning set for a space, it's possible to have two spanning sets give us the same space. So we want to know, well, is it the same space or is it different? So that's the next example we're going to do. We're going to look at two different spans and we're going to see, are these spans the same thing or are they different? In order to do that, you have to show containment both ways. So if I want to show that U and W, for example, are the same, I have to show that W is contained in U and I have to show that U is contained in W. So let's see this in action, working through an example. All right, folks, so here's our example. I wrote it over here so we would have a lot of space to work through this problem. But this is example 17, and we're going to start out by letting P and Q be polynomial functions. We don't know what their degree is, so these live in like P sub n, right, for some n, right, whatever their degrees are. U is going to be the span of those two polynomials, and W is going to be the span of P minus Q, excuse me, and 2P plus Q. And we need to show that U is equal to V. So to help us out here, or to do this, I guess, we have to show that U is contained in W, and we have to show that W is contained in U. So I'm going to do the much more difficult direction first, so we can use all our brain power doing that, and then we'll do the easy direction after that. So the tougher one is showing that U is contained in W. So that's where we're going to start. So we need to show that U are a subset of W. In order to do that, we have to show that the two elements of U are linear combinations of the elements of W. So because of that, what I'm going to do to start out with is I'm going to write kind of a generic linear combination of elements in W. So an element of W looks like. Now, because we're a span, we're a linear combination of these beasts. So we're going to be some value times this first vector. So it's going to be A times P of T minus Q of T plus something times this second vector. So plus B times 2P of T plus Q of T. So this is what we are going to look like. And we need to show that P of T, like we can find an A and a B so that this beast will just simplify to P of T. And then we have to find another A and B so that this piece will simplify down to Q of T. That's where we're headed. That's what we need to do. We need to do that because those are the two defining features of U. Okay. So to help me out, I'm going to kind of rearrange this a little bit because we're interested in showing equaling P of T or equaling Q of T. I'm going to rearrange this so the P of T's are grouped together and the Q of T's are grouped together. So I'm going to first expand the whole thing out. So this is going to be A P of T minus A Q of T plus 2B P of T plus B Q of T. And then grouping my P of T's together, I'm going to get A plus 2B P of T, right? That's A plus 2B P of T plus, and now we have negative A plus B Q of T. So that's what a linear combination in W is going to look like. So we have to check to see if P of T is there and if Q of T is there. So let's check P of T first. So if I have P of T equal to A plus 2B P of T plus negative A plus B Q of T. This is really similar to when we're looking at polynomials and we have like x squared, x, and then the constant term. So now, instead of x squared, we've got P of T, and instead of x, we have Q of T. So to equal P of T, this coefficient is a 1. So I know that this coefficient has to equal a 1 as well. So we need A plus 2B to equal 1. And then we need this coefficient to equal 0 because there's no Q over here. So we need negative A plus B to equal 0. Now, if you wish, excuse me, if you wish, you can use a matrix to solve this. But it's actually much easier just to solve this for B and then plug into here and solve that way. So that's what I'm going to do. From this equation here, this means that B is equal to A. So up here, let's substitute in, we'll put B in for A. So that'll give me B plus 2B is 1. So that means that 3B is 1. So that means that B is 1/3. And since A and B are the same, that means that A has to be 1/3 as well. So what this means for us is that this element P of T, which lives in U, so P of T can be written as 1/3, that's our A, times the first vector of W, which is this beast, plus B, which is 1/3, times the second vector of W, which is that one up there. Therefore, P of T is an element of W because we can write it as a linear combination of its defining pieces. So I'm going to ask you to pause the video here and try and do the same thing for Q of T. See if you can find a way to find values for A and B to show that Q of T is also in W. I'm going to work through that on my own. And then when you're done, you can unpause the video and my work will be on the board and we can check and go through it. So make sure you take a moment to do that and yeah, and then we'll check. All right, so how did we do at showing that Q of T is contained within W? Did you do it? So here's what I did to show it. So I started out the same way. I said, okay, well, let's say that Q of T is a linear combination of the elements in W. So remember, we could rewrite it in this manner. So I just have it set up this way. And then I set up my coefficients the same way as I did here, but now I need there to be a 0 in front of P of T, and I need this to be a 1 in order to equal Q of T. So I have A plus 2B is 0, and negative A plus B is 1. So this time I actually started with this first equation, and I moved the 2B over to see that A had to be a negative 2B. And then I could substitute that in here. So negative 2B gave me 2B plus B is 1. And when I solved this, I got that B had to be 1/3, which then I could plug into this equation to give me that A is negative 2/3. So therefore, Q of T is negative 2/3 the first vector of W, plus 1/3 the second vector in W. And so Q of T is in W, it's in that span. And if you are concerned or you want to check your work, you absolutely can, right? So this would give me negative 2/3 P plus 2/3 P, which is 0P. Negative, so this will give me a positive 2/3 Q plus 1/3 Q is 3/3 or 1Q. So this will in fact simplify to be Q of T. Same thing's true. We could have checked our work here for P of T as well, and we'll see that we would get P of T with 0 Q of T. So this is where theorem 9 is going to come into play. So theorem 9 says that in order to show containment, you don't have to check every possible thing in the set. You just have to check its defining features for its span. And because spans are subspaces, everything's good here. We're following the conditions of our theorem. So therefore, our defining features of U are contained within W. So therefore, at the end here, so right, this is like all going down here. So down here, I would be writing, therefore, U is a subset of W. So we've shown containment in one direction. So to finish this example, we have to show containment in the other direction. So now, instead of showing that U are contained in W, we have to show that W is contained within U. And like I said, I did the really tough one first, so this one should be much easier. So we have to show that W is contained in U. This is much easier because the elements of U are just P and Q. So when I start out with this piece, P of T minus Q of T, well, that's equal to 1P of T plus a negative 1Q of T. So one of these plus negative one of these, that's a linear combination of these two. So that is an element of U. So we already know this is an element of U. So here we don't have to mess with the A's and the B's because our defining set for U is so simplistic, and our elements of W are basically defined as a linear combination of them. So since they're a linear combination of the objects that define the span, they have to be in the span. So same thing for the second one, 2P of T plus Q of T. That's going to be 2P of T plus 1Q of T, which is an element of U. Therefore, W is a subset of U. And that's it. So since we've shown that U is a subset of W and W is a subset of U, U and W are equal. There we go. So that's it for this example. So in fact, that's going to be it for this video. In our next video, we're going to be looking at some special types of subspaces. So in particular, we're going to look at what are called the trivial and non-trivial subspaces of a vector space. And then we're going to take a moment to look at some subspaces that we can grab from matrices. So we're going to look at things like a row space and a column space and a couple of other spaces for those matrices as well. So I'm looking forward to seeing you there. Thanks for watching and have a magnificent day.